This is the Amargosa Desert in California. It's near Death Valley. As you can probably tell from this picture, it's not a good place to be a fish. Nonetheless, in the middle of the Amargosa Desert, there is a cave. And at the bottom of the cave, there is a pool of water. And in that pool of water is the only population of a fish called the Devil's Hole pupfish. There are no other pools of water anywhere around, and even if there were, the only way a Devil's Hole pupfish could get to one of them is if it could fly. In the real world, populations are rarely completely isolated from one another. Yet there are populations like the species of the Devil's Hole pupfish, but usually individuals enter populations and leave them, and that changes what a population looks like genetically. Let's consider what happens when you've got one-way migration. That is, individuals from some source population travel to a destination population. Nobody ever goes the other way, so the source population doesn't change, but the genetics of the destination population can. Okay, here's the basic message of what happens when you've got one-way migration. Migration makes the source, or makes the destination population, in this case the island population, look genetically like the source, which is in this case the mainland. So if you've got migration going from a mainland to an island, genetically the island population is going to start looking more and more like the population that's on the mainland. If this keeps going, if this keeps happening, eventually the population on the island is going to look exactly like the mainland population, genetically. Let's make this a little more precise using a simple mathematical example. When you're having trouble wrapping your head around an idea, particularly when math is involved, it often really helps to start with a simple example, one where you can do the math really easily. Let's say that you've got a mainland here where the frequency of the A1 allele is 0.8, and you've got an island over here where the frequency is 0.6. And let's suppose that a very large number of mainland individuals migrate over to the island. At first you had 1,000 individuals of, say, some bird species. Let's call them, what should we call them? Terns. We're going to call them terns. There are some terns living on this island. There's 1,000 of them. And all of a sudden 1,000 more terns from the mainland show up on the island. What is that going to do to the island genetically? Well, it's pretty easy to tell, because what's going to happen is 50% of the individuals on the island after migration are going to be from the mainland, and the other 50% will have been from this population, the original inhabitants of the island. You can call the migration rate or the migration percentage K. That's the percentage of the island that consists of new immigrants right after migration. What that's going to do is it's going to pull the allele frequency on the island 50% of the way from what it is here toward what it is over here. Okay, so the island individuals, those 1,000 island terns, in them the frequency of the A1 allele is 0.6. And all those 1,000 terns that just showed up, the frequency of the A1 allele is 0.8. That's going to pull the allele frequency of the island halfway toward the allele frequency on the mainland. There it is. The new allele frequency on the island is going to be 0.7. This works for any amount of migration, which is to say any value of K. So here, for example, is that 10 and 90%. Again, we start off with 0.6 is the allele frequency for the A1 allele on the island. It's 0.8 on the mainland. And this time, migration is only going to pull the allele frequency a little way, 10% of the way, up toward this level. what's going to result is you're going to have a frequency of 0.6, frequency of the A1 allele of 0.62. And you can see that's only a little bit higher than it is over here. I mean, that makes sense. Now, if migration is one way, if it's always going from the mainland to the island, then allele frequencies are always sort of pulled toward this set of frequencies over here. And when you've got a really huge mainland and a little small island, that's effectively what happens, because this population is so large that it can absorb any number of terns that try to fly over from the island without really changing genetically. So another take-home point is this. No matter how small migration is, if migration keeps coming over and keeps coming over and keeps coming over from this mainland, eventually the population on the island is going to look just like the mainland population. The frequency of A1 will go to 0.8. Okay, it is different when migration is going both directions. And what that does, if you've got two populations that are both comparable in size, what's going to happen is migration is going to pull the allele frequencies toward one another, and they're going to meet somewhere in the middle. So if these were two islands in roughly equal size, say there's 1,000 terns on this island and 1,000 terns on this island, then what would eventually happen is that they'd equilibrate. You'd reach a point where the allele frequencies on the two islands are the same, and it would be essentially halfway between the two, assuming that you've got equal amounts of migration going both directions.